Hello, everyone. Thank you for watching today. This is my final presentation for ECE570. And what I'm showing here today is implementation of both a physics-informed neural network as well as a method of tuning the atom optimizer hyperparameters in order to yield better results on fewer training epochs. So a lot of the structure and the architecture for the neural network is similar to what we've seen so far in class. The network uses PyTorch, and a lot of the packages are standard to what we've used before. This all is able to run reasonably fast on the Google Colab standard CPU, so not a lot of heavy computation. Although the final grid search takes about 30 minutes to run per model. So what we see here now is the PINN itself. So we have three hidden layers and an output layer using sigmoid activation functions. And what makes the neural network physics informed is really the loss functions. So here we see three. We have a standard loss function for the differential equation, and the equation I've chosen to solve here is the heat equation, and this just calculates the mean squared error of the heat equation, and we can use our standard neural network gradient functionality to calculate our derivatives instead of using numerical differentiation, which can introduce error into numerical solvers. And the other two loss functions cover the initial condition and the boundary condition. So the initial condition we're implementing here is a simple sine wave, whereas the boundary condition is just a constant zero boundary condition on both sides. And our training function is very similar to what we've seen in class so far, although our total loss is calculated by summing up our three separate losses, and I've chosen here to weight the heat equation loss 5 times higher than the other two, since I care more about the performance of the network over the body of the input space, as well as we have a lot more training points along the boundary and initial conditions. So, and then we have two functions that display the solution and return the mesh. So here we can see the results from the standard atom optimizer, in which for the sine wave we have a peak of heat and a peak of cold, and those slowly dissipate over time. And we can see our loss decreases over the full training. And for the optimized optimizer, we have sets of hyperparameters for the atom optimizer. And for each of these sets, which is 108 combinations in total, we create a model, we train it on fewer epochs, but still takes a while, and calculate final losses for that model. And then we aggregate over all 108 combinations to see which model performs the best. And if we get a very similar output, but when we compare our basic to our tuned optimizer, we can see that it achieves a similar loss rate in about a quarter of the epoch counts, and its final loss rate is over a full order of magnitude less than the basic optimizer. So that's what we're showing here, and here's the numerical solution, and we can compare both our basic and our tuned optimizer results to our numerical solution, which acts as our baseline. And I've done all this for a second set of conditions, and this architecture is super nice because we can just redefine the initial and boundary condition loss, and now we have a whole new set of conditions just by changing what we define here. So as you can see, the new output is a constant cold and a gradual heat soak from the walls into the system. And here we get slightly different results, in which our tuned optimizer decreases in loss a lot quicker, but because it features a higher learning rate, it actually has higher variance than the basic optimizer. So it could be argued here which one is the best, as you save on some computation, but your learning rate is so high that you end up with a very similar final loss condition. And then here again is the comparison to the numerical solution. But that's all I have to show today. Happy to answer any questions if there's a way to do so anonymously. Thank you.